Hi, this is Math 2510, and this video is over section chapter 3.6. We're going to look at derivatives of rates of change. And the thing with derivatives is they are rates of change. Any slope is a rate of change when you start looking at it in the context of an application. For example, we look at pay rate. At this. So we may look at pay rate, and it's how your pay changes over time. It's a rate of change. And if we were to look at a function of pay, but like your total pay, so total pay is equal to your pay rate times your hours you work. If you take the derivative of this, you'll get your pay rate. So the derivative of the total pay, the xdt of the GP for total pay, is going to equal your pay rate. Now we're going to start with looking at physics application with this. And that's going to be linear motion or rectangular linear motion. And resembles a motion of an object on a straight path, a specific path that has that follows a line, so you're not turning backwards and forwards. And so we use the function to represent the position. So we call that position function. Now let's consider a particle that can move in either direction as denoted by S of t. S represents the position of the function, the position of the particle on the line at time t. And of course, we'll call this graph the position function. And your particle is to the right of the origin. And if s is less than 0, your particle is to the left of the origin. Think of this as a number line. That's your origin. Move to the right. You're positive units away. If you move to the left, you're negative units away. If we were to take the derivative of the velocity function, then we will find a rate of change. And we will find that that is the rate of change of the position function. Which is going to be your velocity function. Now, velocity. We'll measure that in meters per second, feet per second, just any kind of distance per time. So miles per hour, for example. We can look at the average velocity, which is just going to be your position at time t plus some change in t, delta t. Triangle means called delta, and it just means change of minus your original position at time t over the change in time. And that'll be your average velocity. The instantaneous velocity, on the other hand, is the limit as that delta time goes to 0 of your average velocity. So of s of t plus delta t minus s of t over delta t. So your instantaneous velocity is going to be the slope of your tangent line to your position versus time graph. And so it's the velocity at any point on your um, position function graph. If the object is stopped, then we'll also call this s prime of t, or we'll call this v of t, either one, velocity function or derivative of the position function. But s prime of t will equal 0 if it's stopped. Prime of t equals 0. If it's moving to the right, so let's go back up to this picture, moving to the right here, and you're moving towards the positive side. So your s prime of t is greater than 0. And if you're moving to the left, you're moving towards the negative side. So your s prime of t less than 0. Now, if we continue taking derivatives and we take the next derivative, we get the rate of change of your velocity function. Which is your acceleration function. We'll measure that in some distance per time squared, meters per second squared, feet per second. So it's how quickly a particle picks up speed or loses speed. It's how its speed is changing, is your acceleration. So we'll look at this as the average acceleration is s prime of t plus delta t minus s prime of t over delta t. That's the average. Instantaneous acceleration is the limit. Delta t goes to 0. S prime of t plus delta t minus s prime of t over delta t. We'll call this s double prime of t, or you can write it as a of t for your acceleration function. If your velocity is constant, then s double prime of t equals 0. And this could be constant, meaning stopped, or, and that's when v equals 0, or it's just not increasing or decreasing speed. It's a constant velocity, which means v equals some number. Okay? Not a function, it's actually a specific number. We should know we take derivative of a number, you get 0. Your acceleration becomes 0. If your velocity is increasing, then your acceleration is greater than 0. If your velocity is decreasing, and your acceleration is less than 0. Now, specifically, this is referring to velocity. Right. Speed tells us how fast a particle is moving, and this is regardless of direction. It doesn't matter which way you're going, it's just how fast the number. This is always positive. And so we find speed as the absolute value of your velocity function. absolute value of s prime of t. And we can find the average speed, vf minus vi, over that change in t. Now, with speed, when you think of a car, I follow a car here, and let's make this the back end, a little more flow on it so we know that's backwards. Okay. So, forwards, takes a minute to save now. Okay, forward, and this way is backwards. Backwards meaning negative, forwards meaning positive. Okay. So in a car, you can press the gas and move forward. And so you're pressing the gas means you're accelerating. A is greater than 0. And you're moving forward, so your velocity is greater than 0. So that would be, your speed would be increasing. You can also be going backwards, which means maybe you're pressing the gas and you're going backwards. So by pressing the gas and going backwards, your acceleration is greater than 0. This has to do with acceleration. I'm sorry. Hold on a second. You're pressing the gas, but you're going backwards. Your acceleration is less than 0, and you're going backwards, so your velocity is also less than 0. Everything's in this direction. So acceleration's this way when you're going backwards. Velocity is this direction when you're going backwards. Okay, but they're both negative because it's the direction. So you're going in the negative direction, but you're increasing speed. Okay. Notice that whenever the acceleration and velocity match the signs, both positive or both negative, that's when you're increasing speed. Now, you could be going forward, the velocity is greater than 0, and braking, so acceleration is less than 0, it's the other direction, and so that way you're decreasing speed. So acceleration less than 0, velocity greater than 0. And you can be backing up, so you're going, velocity is less than 0, you're going in the reverse direction. But you're braking, so your acceleration here is actually greater than 0. Because in this case, when you're going backwards, your acceleration is going to be the opposite. So A would be greater than 0, but V would be less than 0. So whenever the opposite signs, your speed is decreasing. So let's look at a situation now. People learn how a balloon, or decides to throw her bouquet of flowers, and she throws it in a path that follows the function here. G is in seconds, S is in meters. And so first we want to know how high the balloon is when she throws it. So let's draw a little picture first. Here's the balloon. It's tossed out. And it does follow parabola path, quadratic equation there, upside down quadratic equation. But that's because this is negative b squared. And so the highest it's going is going to be that peak. Okay. So first, we want to find how high was it when it was first tossed. That's going to be at time equals 0. So find s of 0. And all these terms wipe out. So s of 0 equals 85. So it starts out at 85 meters. And then you want to find the velocity function at time t. So find the velocity, we just take the derivative. So this is just a polynomial quadratic, so we just do the power rule for each of these terms. So s prime of t is equal to v of t. That's going to be equal to negative 9.8 t plus 32. Right, so now we want to know the velocity at 2 seconds. So we'll find v of 2. Negative 9.8 times 2 plus 32. Let me pull up a calculator here. So negative 9.8 times 2 is 32. You're at 12.4 meters per second. Now we want to know what the maximum height reached. Well, at that maximum height, your velocity goes to 0. Okay, so we can find by setting our velocity function equal to 0. So we will have negative 9.8 t plus 32 equals 0. And then 9.8 t equals 32. And then divide by 9.8. 32 by 9. I get 3.26. 2.27 seconds. But we want to know how high it goes. So we have to go back up to our S of t and plug in 3.2 seconds. We're going to probably do this a couple of times with different values, so I'm going to actually put the function in. Negative 4.9 squared plus 32x plus 85. Now we'll go to our table and type in 27. Let me set the 27. You get 137.24 meters. All right. So now we want to know, when is the bouquet's position increasing? So increasing would mean that the velocity is positive. So let's look at the velocity equation again. We always solve this for s equals 0. That is when it's at 3.27 seconds. Now, we can intuitively look at this as it goes from where it was tossed and to the top of its height. It's decreasing in um, in speed, right? So if we can test some values here. So you plug in 1 for t, we'll have negative 9.8 plus 32. You're going to get a positive value there. And if you plug in 4 for t, you'll have something well enough above a negative 32, and so you end up with a negative value here. Okay. So your velocity is negative. Negative on this side, positive on this side. So when it's see how I want to go about this. So increasing is when it's going higher. Okay. Higher meaning that it's above where it was tossed and moving upwards. Right, so it's still increasing when it's positive. That's going to be from 0 to 3.27. Okay. It's decreasing coming back down. That would be after the 3.27. And then when is the speed decreasing? Well, we would have to look at our acceleration. So A of t equals a negative 9.8. So we have 3.27, and you have velocity is positive, velocity is negative on both sides. Your acceleration is always negative, negative, negative. Okay? Remember, decreasing is when it's opposite signs. So acceleration is negative, velocity is positive. That also is between 3.27. If you think about it, it's slowing down as it goes up to 0. Okay. The next one is you have a car, and it's going to follow the function here. S of t is 2t to the third minus 9t squared plus 12t minus 4. Again, S is in meters, t is in seconds. Find the time when the car's position is increasing, moving to the right to find your derivative. We'll have 6t squared minus 18t is 12. And we can factor out 6. And we can factor this. Will be, let's see, t minus 2, t minus 1. That's your derivative, and you want to get when this is going to be equal to 0, equals and t equals. Anyways, line, and we can look at different points here. If it's 0, that would be you'll have a -2 and -1, which would be positive. Two negatives make a positive. If it's 3, you'll have a positive and positive, positive. And then if it's like 1.5, 1.5 minus 2 would be negative, and 1.5 minus 1 would be positive, so you have a negative in the middle. So again, it's moving to the right when it's positive, so it's going to be before 1 second and then after 2 seconds. So before second, after 2 seconds. So we want to find the time when the velocity is increasing, so we'll find acceleration. We'll set that equal to 0 and find t is equals 18, 12. It's going to be, let's see, 9 over 6, 3 over 2. Acceleration, here, 5. So if acceleration is 0, or I'm sorry, time is 0, you'll have a negative acceleration. Time is 2, you'll have a positive. So your velocity is increasing after 5 seconds. But find the time when the car speed is decreasing. So we'll line these up now. Velocity on top, acceleration on the bottom. We got 1, 5, 2. Velocity is positive before 1, positive after 2, negative in between. Acceleration is positive after 1.5, negative for that. Again, decreasing is whenever they are opposite. So it's decreasing before 1 second and between 1.5 and 2 seconds. Next one is SEO is going to try to catch up to them at the origin. Are they moving away or towards the origin at time 0.5 seconds and 1.5 seconds? Now, I'm going to go a little bit more into this one. I'm going to look at the position, P for position, but use SFT and time. And origin would be basically the x-axis. So are they moving away or towards the x-axis? So at we'll have 0.5 and we'll have 1.5. Let's find the values, positions for those two. 5, 5, 99. Oh, do I have the same one I had before? No, I don't. That's this. 2 cubed minus 9x squared plus 12x minus 4. So about 0.5 on the origin. At 1.5 there above the origin. Now let's look at the velocity of doing at these points. So I'll type this in since it's going to save anyways. 6 minus 2 x minus 1. So let's see. Velocity is 4.5 at 0.5. That's moving up. And is negative 1.5. So it's moving towards the origin. So at equals 0.5, we're moving away. At t equals 1.5, moving towards. So we won't find the total displacement that the car travels from t equals 0 and t equals 4 seconds. So basically at 4 seconds is the position. We'll find S of, and so we'll plug in 4. And you get positions y1, so it'll be 28. And we want to find the car's average velocity between 0 and 4 seconds. So, I'm sorry, average speed. So average speed is v final minus v initial over change in t. Change in t is easy, it's 4 seconds. We want to find speed at 0 seconds. It's 12. That's your initial. At 4 seconds, we plug that in, it's 36. We get 24 over 4, so we get 6. Alright. Alright, so let's look at some graphs now. In this particular graph, we have a bug is crawling on a straight wire. The velocity v of t of the bug at time t, 0 and 11 seconds, is given by the graph below. We're going to dissect each area. So first, let's just figure out what's going on. So this is the velocity. So anywhere where the velocity is constant means acceleration is 0. Acceleration 0 here, acceleration 0 here. So that's why the velocity is constant. Now, if the velocity is constant, then you're moving at a constant linear rate. Now, everywhere above the x-axis up to this point, velocity is positive. So your position is increasing. Below this point, your velocity is negative. position is decreasing. So let's see what they're asking for. At what time t does the bug change direction? This is going to be when it goes from positive to negative. So this is going to be at t equals 8. Velocity changed times. At what time t is the speed of the bug greatest? So greatest speed is only the point that has the highest value. So on the top, we have 2 seconds. It's at velocity 3. Velocity equals 3. Bottom, at 10 seconds, you have velocity of negative 4. So velocity equals negative 4. But it's asking for speed, and we take the absolute value. So v1 velocity equals 4. Speed at t equals 10. When is the bug moving to the right? When is it moving to the left? Right being increasing position, positive velocity. So right is between 0 and 8, is between 8 and 11. When is the bug's acceleration positive, negative, 0? So acceleration being positive whenever it's going, your slope is positive. So here is when acceleration is positive. It's negative, constant, negative, positive again, constant, negative, and positive again. So those 3 spots are positive. So 0 to 2, 5 to 6, and to 11. 0 to 2, 5 to 6, and to 11. Positive. Negative, that's going down. So 2 to 3, 4 to 5, 7 to 10. 2 to 3, 4 to 5, 7 to 10. Then constant is when it's 0. We already labeled those. 3 to 4, 6 to 7. Right, so graph the bug's speed. Now, good thing is the graph looks pretty much the same. Goes from 0 to 3 to it's pretty much the same until you get to the other it gets a negative part. So it drops down 1, then goes constant for 1 second, then drops down 1 again, then goes up 1, then goes constant. Then at 8 seconds, it will be at 0. So it drops down to 0. 2, 3, 4, 5, 6, 7. Now, we're talking speed. So the graph basically mirrors everything becomes positive. So it's at a speed of 4 at 10 seconds. That's the speed. Acceleration will follow the slopes. So easiest one, let's do the 0 slopes between 3 and 4. And 6 and 7. So that's those slopes. now we can get the lines here. So 0 to 2 have a slope. So it goes up 3 over 2, so 1.5. Straight line, because slope is a straight line. It's a constant acceleration there. It drops down to a decrease of 1 for a second. Goes to 0. Then it's a decrease of 1 again. Then it's an increase of 1. Then it goes back to 0. Then it's a decrease of 2. An increase, this is 4 and 2. Rise of 4 over 2, so increase of 2 for 2 seconds. And then it's a decrease of 1. It looks like that. So there, and if you really end, highest acceleration is at 2. Um, between 8 and 10, that's in the positive direction. Highest negative accelerations at between 7 and 8, which is also. Next one, you have a particle that's moving along the x-axis, so the velocity between 0 and 6 seconds is given by the graph. Velocity is at 0 at 0 seconds, 3 seconds, and 5 seconds. The graph has horizontal tangents at 1 second and at 4 seconds. Here as well, acceleration equals 0. When does the particle change direction? And this is when it crosses the x-axis. But we're not going to count before 0. We're going to assume that that's when it starts. So it's going to be at time equals 3 and time equals 5. As it changes, velocity changes sign. When does the particle move forward? We want to have a positive velocity. So positive velocity, 3 and 5. And backwards, it's going to be negative velocity between 0 and 3 and 5 and 6. So during what time interval is the acceleration negative? Well, that's going to be when your slope is negative. So when you're going downhill from your velocity curve. So your acceleration is negative here. What's here? It's still downhill. And here. So from 0 to 1, from 4 to 6. When slope velocity graph is negative. And what time intervals, if any, is the speed of the particle increasing, decreasing? So increasing would be when your slope is positive, so that'd be from 1 to 4. So slope. Increasing. That's specifically for the velocity. They did ask for speed. Let's do this. Hold on a second. Do this with the graph. Number line, I mean. So we'll start with velocity since we started this. I said 1 to 4. So velocity is positive. Oh, I'm sorry. Acceleration is positive. Acceleration is negative between 0 and 1. And 4 to 6. 1 to 4, 6, and 0 here. So acceleration is negative there. Now velocity is positive between 3 and 5. 3, 5, and that's when the velocity is positive. So it's negative between 5 and 6. It's negative between 1 and 3. And it's negative between 0 and 1. So increasing. It's while they are the same. So 0 and 1. Different there. They're the same between 3 and 4. They are different here. They are the same between 5 and 6. Increasing between 1 and 3. Between 4 and 5. All right, so let's get into some other little applications. Last application actually. We have what's called a cost function. This is the total cost that a company incurs in producing X units of some product. The average rate of cost is going to be given by your cost function as X plus some initial X plus some change in X minus your initial cost, your change in X. The limit as this quantity as X goes to 0 is the instantaneous rate of cost with respect to the number of items produced. And we call this the marginal cost. This will be C prime of X. So if we are given cost function of 0.01 x squared plus 4x plus 10,000, then we are going to be producing X units. Find the marginal cost, so that's taking the derivative. C prime of X is 0.02 x plus 4. And we want to find what C prime of 300 is. That would be 2.02 times 300 plus 4. Clear it up. 0.02 times 300 plus 4 is 10. Let's add 3 more to that. It's 10. We have prime of 300. 10. And this means that the cost per unit is $10 at when 300 x or you can say it as cost of producing 301 why is it that way? Using the 301st item, $10. That way of saying it. So we're going to compare now the cost of producing the 301st item or gadget with that C prime of 300. So what we're doing here is we're going to look at C of 301 minus C of 300. I'm going to compare it to the $10 we got. So let's put this function in. Putting in our cost function, 0.01 x squared plus 4x plus 10,000. And we'll find 301. And we'll find 300. We have 12, 110 minus 12, 100 equal to 110. Okay, so it matches. Now, if we were to actually go through, there's some rounding going on here in this. So if we were to actually calculate this out, 0.01 times 301 squared minus 4 times 301 plus 10,000 minus 0.01 100 squared plus 4 times 300 minus 10,000. These cancel. When you calculate the rest of this out, you actually end up with so there was some rounding if you using the calculator here, but even so, it is a very good estimate of how much that 301st product to make is. So it's very good estimate. All right. So the next video and this last video in chapter 3 is going to be on related rates. So I will see you then. Bye.